In this outcome, we shift our attention to static electricity, charge that sits still rather than flowing. We'll look at electric fields and forces, then move on to capacitors, how they store charge and energy, and how they charge and discharge over time. Let's begin. Let's start with what static electricity actually is. It's electric charge that's at rest, not flowing as a current, and it builds up when electrons get transferred from one surface to another. Rub a balloon on your hair and the balloon comes away negatively charged, and that charge simply sits there until it finds a path to discharge. Understanding it is what lets us analyze electric fields, the forces between charges, and how charge is stored. Charge is a fundamental property of matter, measured in coulombs. Electrons carry negative charge, and protons carry positive charge. And the golden rule is that like charges repel, while unlike charges attract. A single electron carries a tiny amount of charge, about 1.6 times 10 to the minus 19 coulombs. And charge is always conserved, it's transferred from place to place, never created or destroyed. Let's fix our vocabulary. Charge Q is the quantity of electricity in coulombs. An electric field is any region where a charge feels a force, and the field strength, E, is the force per unit charge, measured in volts per meter or newtons per coulomb. Potential difference, V, is the energy per unit charge between 2 points, in volts. And capacitance, C, is the ability to store charge per volt, measured in farads. An electric field surrounds any charged object, and we picture it with field lines that run from positive to negative and never cross one another. Between two parallel plates, the field is nice and uniform. A closely related idea is the potential gradient, which is how quickly the voltage changes with distance, and in fact the field strength equals that potential gradient. The field strength equals the voltage divided by the distance. So the field strength comes out in volts per meter, with the voltage in volts and the distance in meters. Let's calculate a field strength. Two parallel plates sit 2 millimeters apart with 240 volts across them. The field strength is the voltage over the distance, but first convert the distance. 2 millimeters is 0.002 meters, so the field strength equals 240 divided by 0.002, which comes to 120,000 volts per meter, or 120 kilovolts per meter. A capacitor is a device for storing electric charge on two conducting plates, which are separated by an insulator called a dielectric. The charge it stores is proportional to the voltage applied, and that relationship is beautifully simple. Charge equals capacitance times voltage. Capacitance itself is measured in farads, though a whole farad is enormous, so in practice you'll meet microfarads, nanofarads, and picofarads. Let's find the charge on a capacitor. We've got a 470 microfarad capacitor across a 12-volt supply. Charge equals capacitance times voltage. But first write the capacitance in farads. 470 microfarads is 470 times 10 to the minus 6 farads. Multiply by 12 volts and you get about 5.64 times 10 to the minus 3 coulombs. In other words, 5.64 millicoulombs. Let's look at how a capacitor is built. Two metal plates, or foils, face each other across a thin gap, and a dielectric layer fills that gap and boosts the capacitance. Two things increase the capacitance: a larger plate area and a thinner dielectric. We tie those together in the formula capacitance equals epsilon naught times the relative permittivity times the area divided by the separation. And to save space, those foils are often rolled up into a cylinder. Let's think about the dielectric itself, the insulator between the plates. Permittivity is a measure of how well a material stores field energy. The permittivity of free space, epsilon naught, is a fixed constant, 8.85 times 10 to the minus 12 farads per meter. The relative permittivity, epsilon r, then compares a given material to a vacuum. Common dielectrics include air, mica, ceramic, polyester, and paper, and the higher the relative permittivity, the more capacitance you get for the same size. Let's put numbers into that formula. A capacitor has a plate area of 0.02 square meters, a dielectric 0.1 millimeters thick, and a relative permittivity of 5. Taking epsilon naught as 8.85 times 10 to the minus 12, first convert the thickness. 0.1 millimeters is 0.01 meters. The top of the fraction is 8.85 times 10 to the minus 12 times 5 times 0.02, which is 8.85 times 10 to the minus 13. Divide that by 0.01 and you get 8.85 times 10 to the minus 9 farads, or 8.85 nanofarads. It's worth contrasting conductors and insulators. A conductor has plenty of free electrons, so charge flows through it easily, which is why we use materials like copper and aluminium for plates and wires. An insulator, or dielectric, has very few free electrons and so blocks the flow of charge, which is exactly what we want for the layer between the plates, using materials like mica, ceramic, or simply air. A charged capacitor doesn't just hold charge, it stores energy in its electric field, and it can release that energy very quickly when needed. The energy equals 1/2 times the capacitance times the voltage squared, measured in joules, though you can also write it as a half QV or Q squared over 2C. Notice that because of the voltage squared term, doubling the voltage stores 4 times the energy. That rapid release is exactly what powers a camera flash or a defibrillator. Let's calculate a stored energy. A 1000 microfarad capacitor is charged to 50 volts. Energy equals 1/2 times the capacitance times the voltage squared. Write the capacitance as 1 times 10 to the minus 3 farads and square the voltage. 50 squared is 2500. So the energy is 1/2 times 10 to the minus 3 times 2500, which works out to 1.25 joules. Let's pause for a check. Can you state the formula linking field strength, voltage, and distance? Which two features of a capacitor increase its capacitance? And if the voltage doubles, what happens to the energy stored? Have a think before we move on. Let's see what happens when we charge a capacitor through a resistor from a DC supply. Right at the start, the capacitor is empty, so the voltage across it is 0 and the current is large. As charge builds up, the capacitor voltage rises and the charging current tails off, approaching the supply voltage. Crucially, the voltage doesn't climb in a straight line. It follows an exponential curve, described by V equals the supply voltage times the quantity, 1 minus E to the minus T over tau. Discharging is the mirror image. Disconnect the supply and connect the capacitor across a resistor, and the stored charge now flows out through it. The voltage starts high and falls away towards 0, with the current flowing in the opposite direction to charging. This time, the voltage decays exponentially, following V equals the initial voltage times E to the minus T over tau. In practice, a bleed resistor is fitted to discharge a capacitor safely after the power is switched off. The speed of all this charging and discharging is set by the time constant, written as the Greek letter tau. It's simply the resistance times the capacitance. Tau equals R times C, with R in ohms, C in farads, and tau in seconds. After one time constant, the capacitor has reached about 63% of the full voltage, and after 5 time constants we treat it as fully charged, at around 99%. A larger resistance or capacitance gives a slower response, which is how we design timing and delay circuits. Let's calculate one. A 100 microfarad capacitor charges through a 10 kiloohm resistor. The time constant is R times C, so convert first. 10 kiloohms is 10,000 ohms, and 100 microfarads is 100 times 10 to the minus 6 farads. Multiply them and tau comes to 1 second. Since we treat it as fully charged after 5 time constants, that's 5 times 1, so about 5 seconds. Here's a tidy method for any electrostatics problem. Identify what you're given, whether that's voltage, distance, area, capacitance, or resistance. Sketch the arrangement, be it parallel plates or an RC circuit. Note exactly what's asked for: field strength, charge, energy, or time. Choose the matching formula. Convert everything to SI units before you substitute, and finish by checking the answer is a sensible size with the right units. Let's set charging and discharging side by side. When charging, the voltage rises from 0 up to the supply value. The current starts high and falls to 0. The voltage follows 1 minus E to the minus T over tau, and energy is being stored. When discharging, the voltage falls from the supply value back to 0. The current starts high but flows in reverse before dying away. The voltage follows e to the minus t over tau, and energy is being released. It really helps to match the unknown to the right formula. For the field between plates, use the field strength equals the voltage over the distance. For charge stored, use charge equals capacitance times voltage. For the capacitor's size from its materials, use the epsilon naught, epsilon r, area over distance formula. For energy stored, use 1/2 times the capacitance times the voltage squared. And for the timing of charge or discharge, use tau equals r times c. Match the unknown, then substitute in SI units. Capacitors turn up all over engineering. They smooth the ripple in DC power supplies. They set timing and delays in RC networks. They store energy for camera flashes and defibrillators. They filter signals in audio and radio equipment. And they decouple, steadying the supply to sensitive chips. They even help tune a radio to select one station's frequency. Let's gather the key terms. A dielectric is the insulating material between the plates. Permittivity, epsilon, measures how well a material stores electric energy. The time constant, tau, is the product r times c, and it sets the charge and discharge speed. An exponential curve is the shape of that charging or discharging over time. A bleed resistor is one fitted to discharge a capacitor safely, and the coulomb is the SI unit of electric charge. One more check before we close. Can you write the formula for the energy stored in a capacitor? Can you calculate the time constant for a 4.7 kilo-ohm resistor and a 220 microfarad capacitor? And why do we fit a bleed resistor across a large capacitor? Give those a go.
Let's compare brittle and ductile materials directly. Brittle ones, like glass and cast iron, break with very little deformation, failing by crack propagation, giving little warning and absorbing little energy. Ductile ones, like copper and mild steel, deform plastically before breaking, can be drawn out into wires, rely on dislocations to allow slipping, and tend to blunt cracks and resist them. It's a real contrast in how the two kinds of material give way. A few final key terms. Brittle means it breaks suddenly with little plastic deformation. Ductile means it can be drawn into a wire and deforms plastically first. Stiff means it strongly resists stretching, a high Young's modulus. Tough means it absorbs a lot of energy before fracturing. Strength is the stress a material can bear before failing, and a dislocation is a line defect that lets crystal planes slip. Let's finish with a check. Can you explain how dislocations make a metal ductile? Can you describe 2 ways to strengthen a metal and why they work? How does a crack cause brittle fracture? And using the formula extension equals force times length over area times E, can you explain why a stiffer cable stretches less?